Hi, welcome to my channel. I am Aravindan. This is the 8th lesson in electric field. I mainly focus on Edexcel, Cambridge and international baccalaureate syllabuses, but even the students, those who are following AQA, OCR also can use these lessons. Okay, last class, that is during the last lesson, we learned about electric potential and we derived the equations for electric potential energy and work done in electric field. So in this lesson, I'm continuing that with examples and some calculations. Okay, so if I consider small revision on it, last class we learned the electric potential at a distance of r from a point charge q is given by kq over r. And when we are using this equation, we must include the sign of the charge. I told that last class. Same way, when a conducting sphere or metal sphere consists of uniform distribution of charge on its surface, the electric potential is also the electric potential is given by V equal kq over r, and also we can assume the whole charge is concentrated at its center according to Gauss law. I already explained that earlier also. So the whole charge is concentrated at the center, we can assume like that, and inside the solid sphere at all points it should have the same potential, because if the potentials are different inside it, due to potential difference there will be current flow due to delocalized electrons. That means you are getting electrical energy from nothing, actually without using any power supply. You are getting electrical energy due to the flow of free electrons or delocalized electrons. Why that happens? Because of potential difference between 2 points inside the solid metal. But practically it is not observed. So what conclusion can we say? Inside the metal conductor at all points the potential must be the same, and that must be equal to the potential on its surface. So if you plot a graph of potential against distance is measured from the center up to the surface, the potential is the same as the potential on its surface, so that is kq over r. Then beyond it, the potential will decrease because the potential is inversely proportional to the distance. So the graph will be like this. Same way, if the metal sphere consists of negative charge on its surface, here also we can assume all the charges is concentrated on its center, but the potential is going to be negative. So inside the metal sphere at all points, the potential will be same. That will be minus kq over r. R is the radius, right? Same explanation. At all points, the potential should be the same. Then beyond that surface, outside, the potential will decrease because potential is inversely proportional to the distance. Okay, simple calculation. In space, a 10 nanocoulomb is kept at a point. The question is, find the electric potential at a distance of 20 centimeters from this point. The point P is at a distance of 20 centimeters from this point. So simple, we know the equation. The equation is given by the electric potential V equal kq over r. K, I am using 9 into 10 to the power 9. Q is 10 nanocoulomb, 10 into 10 to the power minus 9, divided by the distance is 20 centimeter, convert to meter, 0.20. So if you solve, that will be the potential at point P, that will be 450 volt. Simple question. Okay, the next question, question number 15. A charge of minus 20 nanocoulomb is kept in space, and the question is, find the electric potential at a distance of 5 centimeters from minus negative 20 nanocoulomb. Same equation, but only thing, we should include the sign of the charge. So potential at P is given by V equal kq over r, k 9 into 10 to the power 9. Q is negative, so minus 20 into 10 to the power minus 9 divided by r is 0.05. So solve it, you will get a negative potential. So that will be minus 3,600 volt. I told that last class. What's the meaning of negative potential? It is an actually when you are bringing a positive charge from infinite distance to this point, actually the positive charge will gain kinetic energy. That's the meaning of the potential with negative sign. Okay, so here a spherical conductor, it's a solid conductor. That means inside also it's metal, nothing, it's not a hollow, it's a solid sphere. Radius 4 centimeter. It consists of a uniform distribution of charge of 5 nanocoulomb on its surface. First of all, find the electrical potential on its surface. So we know we can assume the whole charge is concentrated at its center. If I assume like that, so first part, the electric potential on its surface is equal to kq over r, k 9 into 10 to the power 9, q is 5 nanocoulomb, 5 into 10 to the power minus 9 divided by 4 centimeter, 0.04. So if you solve it, you will get the answer for the first part, that is 1125 volt. That's the first part answer. Second part, find the electric potential at a distance of 1 centimeter from the center. That means that is inside. 1 centimeter means somewhere here. Right? This is 1 centimeter. So we learned that the electric potential inside all parts should be same as the surface, the potential on its surface. So second part, I don't need to calculate. That is same as the electric potential on its surface because it's a conductor. There can't be potential difference. If there is potential difference, then there will be flow of current, flow of free electrons, delocalized electrons will cause electric current, electric energy from nothing. So it's violating the law of conservation of energy. So there can't be any potential difference inside the solid conductor. So that potential also should be same as the potential on its surface. Third part, find the electric potential at a distance of 8 centimeter from its surface. So if it is 8 centimeter, that is at point P they are saying. So if I say this is 8 centimeter, from the center it's going to be 12 centimeter. Same equation, V equal kq over r. So 9 into 10 to the power 9. Charge is 5 nanocoulomb, 5 into 10 to the power minus 9 divided by the distance is 12 centimeter from the center. So that is 0.12. So you will get answer that is 375 volt. Okay, so this is about electrical potential energy. So in this question, they are saying a 20 microcoulomb, a point charge is kept in space at a distance of 5 centimeter from it. Another point charge of 10 nanocoulomb is kept on it. That means this 10 nanocoulomb is in the electric field of 20 microcoulomb. So the question is, find the electrical potential energy of this 10 nanocoulomb charge. So last class we learned the electrical potential energy is given by K Q over R. So 9 into 10 to the power 9. Q is 20 microcoulomb, 20 into 10 to the power minus 6 into, this is 10 nanocoulomb, 10 into 10 to the power minus 9 over, distance is 0.05. So solve it, you will get the answer, that is 0.036 joules. So it's better to go through watch the previous video because they are explaining about what's the meaning of positive electrical potential energy, what's the meaning of negative electrical potential energy. All I explained in that one. So better go through that previous video to get the idea of what's the meaning of positive electrical potential, right? Better go through the previous video. Okay, so here PQRS is a square in space, right? It's a virtual square. So On each side, the length of each side is 10 centimeter. A point charge of 20 microcoulomb is kept at point P, and a point charge of minus 6 microcoulomb is kept at point S. The question is, find the electric potential at point S. So you know that electric potential is a scalar quantity. So since it's a scalar quantity, there's nothing to find direction or anything. Just find the electric potential created by 20 microcoulomb at point S and the electric potential created by minus 6 microcoulomb at point S and just add it. So it's a scalar quantity, no direction. So I can say electric potential and electric potential at S equal potential due to this one is, you know, K Q1 over R1 plus K Q2 over R2. That's a general format. So 9 into 10 to the power 9, Q1 is 20 into 10 to the power minus 6 over R1 is the distance 10 centimeter, 0.1 plus 9 into 10 to the power 9. You know we should include the sign of the charge, that is minus 6. So minus 6 into 10 to the power minus 6, that's a micro, 10 to the power minus 6 over the distance is again 0.1. So solve it, you will get the final electric potential, that will be 1.26 into 10 to the power 6 volt. Okay, so in this question, X and Y are 2 points in space and there is a point charge, 2 microcoulomb is kept at X and a charge of positive 8 microcoulomb is kept at Y. So there's a point on the line XY, that is P. The distance of P from X is 2 centimeters and from Y the point P is at a distance of 4 centimeters. So first part, find the electric field strength at P. So we know if I keep a positive test charge, that will be pushed by X. So the electric field strength due to 2 microcoulomb at P will be this direction. I can name it E1. Same way, the direction of the electric field strength due to 8 microcoulomb at the same point P will be this direction. I can name it E2. So the E1 and E2 are in opposite direction and we know that electric field strength is a vector quantity. So if I want to find the resultant electric field strength or net field strength at point P, I should find E1 and E2 and subtract the smaller one from the larger quantity, right? So I'll find it first part. I can say the net electric field strength is equal to, I'll take it E1 larger. I don't know, I'll solve it. If I get negative answer, I can change the direction towards left. So E equal, I'll take it E1 minus E2. That is K Q1 over R1 squared minus K Q2 over R2 squared. That is 9 into 10 to the power 9. I'll take it common. Q1 is 2 microcoulomb. 2 into 10 to the power minus 6 over R1 squared is, this is 2 centimeters. So 0.02 minus Q2 is 8 microcoulomb. 8 into 10 to the power minus 6 over, that is Py is 4 centimeters. So 0.04 squared. Solve it. You will get 0. That means point P is a null point or neutral point. Okay, we'll find what can be the potential at P. So is it necessary to be 0? The potential also, should it be 0? We'll find it, right? So second part, we'll find the net potential at V. You know, that is a scalar quantity. So I can say K Q1 over R1 plus K Q2 over R2. So K is 9 into 10 to the power 9. I'll take it common. Q1 is 2 microcoulomb. 2 into 10 to the power minus 6 over R1 is 0.02 plus, we just add it. Only thing we need to consider the sign of the charge. Both are positive charges. Q2 is 8 into 10 to the power minus 6 over that is 0.04. Solve it. How much will you get? You will get 2.7 10 to the power 6 volt. That means it's reasonably larger voltage. See, it's a neutral point. So some students have, I don't know why, wrong idea. They think at a point, if the potential is if the field strength is equal to 0, that is, if it is a neutral point, then the potential at that point also must be 0. No, that is wrong, right? You can see that here electric field strength is 0. Point P is a neutral point, but it has a potential, a reasonably larger potential. Okay, how is it possible the point P has no electric field strength but there is potential? How is it possible? Okay, electric potential is given by E equal minus dV over dx. That definition is not used in A-level syllabus, but better know that E equal minus dV over dx. Right? So that is electric field strength is the derivative of voltage with respect to x. So if I plot a graph here, voltage against x graph, this is happening. Voltage against x graph, that is x is measured from this capital X. Okay, if I say x is measured from capital X. So what's happening actually, at this particular point, there's a voltage that is this much. If you try at home, if you want, you can try it. Take a point which is slightly on left side. Say maybe 2 millimeter towards left. That means find the electric potential at a point that is at a distance of 1.8 centimeter from X, right? Find the electric potential. Again, find the electric potential at a point which is on the right side of P, that is 2.2 centimeter from P. You will see the actual reason. You can see that the graph is something going like this. So at this point P, this is the point P at which you got a voltage of this much, 2.7 10 to the power 6 volt. If you find the same voltage, this is at point at a distance of 2 centimeters. If you find the voltage at a point slightly on left of point P, that is at a distance of 1.8 centimeter from X, you will see there will be a voltage somewhere here, that is something, you will get 2.71 10 to the power 6 or something like that. Yeah. Same way, if you find a voltage at 2.2, you will again get a voltage that is more than this value. So at 2 centimeter, that is 2.7 10 to the power 6, but at 1.8 and 2.2, the voltages are more than 2.7 10 to the power 6. That means the point at 2 centimeter distance from X, there is a turning point. So you know, for a turning point, the derivative is 0. dV over dx is 0. That's the reason you are getting electric field strength 0 at that point. Okay, in terms of graph, I explained that. Okay, next question. A charge of 20 nanocoulomb, a point charge, is kept at point in space. X and Y are two different points. They are 12 centimeter and 8 centimeter respectively from this 20 nanocoulomb charge. First part, find the electrical potentials at X and Y. So I can find separately the potential at X and Y. We know the equation V equal KQ over R. So Vx equal 9 into 10 to the power 9. Q is 20 into 10 to the power minus 9 over the distance of X is 12 centimeter, that is 0.12. So that will be 1500 volt. Same way, Vy equal 9 into 10 to the power 9 into 20 into 10 to the power minus 9 over Y is at a distance of 8 centimeters, so that is 0.08. That will be 2250 volt. Okay, third part, they have to find the work done. Find the electrical work done when a point charge of minus 5 microcoulomb moves from X to Y, right? So we know that work done is given by W equal Q times delta V. Delta V is the potential difference between X to Y, X and Y. But last class I told that when you consider potential difference, since the charge is moving from X to Y, that should be Q into Vy minus Vx. Last class I derived it, right? In my previous video, that is lesson 7, I derived it. The work done is given by W equal Q times delta V. Delta V means from where to where is it moving? It's moving from X to Y. So Vy minus Vx. Now, when you are using this equation, you must use the sign of the charge as well as sign of the potentials of those points. If those points have negative potential, then you should use the negative voltage. But here, both potentials positive, so they are going to be positive, but the charge is negative, minus 5 microcoulomb. So minus 5 into 10 to the power minus 6 times Vy. Vy is 2250 minus Vx is 1500. Solve it, you will get the work done, that will be minus 3.75 into 10 to the power minus 3 joules, that is minus 3.75 millijoule. Okay, so third part, they're asking whether will this charge gain or lose energy during this motion. That also I explained in my previous video. That means if the work done is negative, that means the particle, that moving charge particle, will gain kinetic energy and lose electrical potential energy. Please go through the previous video, right? So here they are asking, will this charge gain or lose energy? That means they are saying energy, but actually kinetic energy will lose, gain or lose actually kinetic energy, just not the total energy, kinetic energy during this motion. So it will gain kinetic energy. Okay, so the third part, it will gain kinetic energy. So since the work done is a negative quantity in this calculation, it will gain kinetic energy and lose electrical potential energy. Okay, it's an interesting question. In this question, they are saying there's a nitrogen nucleus. Towards it, an alpha particle, alpha particle is the helium nucleus. Its charge is plus 2 times the charge of an electron, but it's positive, right? So it's moving towards the neutron at a speed of 1 into 10 to the power 7 meter per second, right? So when it moves towards it, we know that it's going to experience an electrostatic repulsive force, because alpha particle is also positive, nitrogen also positive, so they are going to repel each other. Alpha is a helium nucleus, its charge is plus 2 times charge of an electron, but it's positive, so it's going to experience electrostatic repulsive force, so it's going to lose its kinetic energy. So they are saying initially we are going to assume it was much far away from the nitrogen, so it won't experience any electrostatic force at that point from where it's moving towards the nitrogen. So when it moves towards nitrogen, it's going to lose kinetic energy and gain electrical potential energy. So at point C, we take at point C, it comes to rest. Then it will be bounce off, but it comes to rest at point C. If I throw this pen vertically upwards, it will slow down and reach a highest point at which it will have the highest gravitational potential energy. Then it will fall down, right? Same way, it's going to slow down at point C it comes to rest, then it will go back. That's a different story, but it's going to come to rest at point C. So when it moves from far distance, initially it had a speed of this much, it's going to lose its kinetic energy. At point C, its kinetic energy will be equal to 0, and all the loss in kinetic energy will become equal to electrical potential energy. So we are going to use that equation, loss in kinetic energy equal to gain in electrical potential energy. Okay, so I can find the initial kinetic energy of the alpha, that is equal to half times its mass is given 36.8 10 to the power minus 27 times its initial speed before comes to rest, 1 into 10 to the power 7 all the squared. So you will get answer that is 3.4 10 to the power minus 13. Okay, so we'll take it comes to rest by losing all its kinetic energy. It comes to rest at point C, so it will have the maximum electrical potential energy at point C. So it's I can say it comes to rest at C, and its electrical potential energy is given by K Q over R, because it's moving in the field created by the nitrogen. So that's the charge of the nitrogen. This is the charge of alpha particle. So K is 9 into 10 to the power 9. Charge of the nitrogen is given 11.2 10 to the power minus 19. Charge of the alpha particle is given 3.2 10 to the power minus 19. Over the distance r is unknown. So we are going to find that one. So I can say loss in kinetic energy, gain in electrical potential energy. It's losing the kinetic energy, so it's going to gain electrical potential energy. So that is 3.4 times 10 to the power minus 13 is equal to, I'll write again, 9 into 10 to the power 9 into 11.2 into 10 to the power minus 19 into 3.2 into 10 to the power minus 19 divided by R. So solve it, you will get the value of R up to what distance is going to be closest to the nitrogen. You will get an answer 9.4 10 to the power minus 15. That's the final answer. Okay, so it's a good question to understand the conservation of energy, loss in kinetic energy equal gain in electrical potential energy in electric field also. Okay, I hope you understood all these questions. In my next video, I'll discuss about equipotential surface and how to draw the equipotential surface and its properties, and some questions related to equipotential surface. Then the following video after that, that is the video 10th video, this is the 8th one. 9th one I'll do about equipotential surface. Then the 10th video I'll discuss some past paper questions from Edexcel. Then 11th video I'll discuss some past paper questions related to electric field from Cambridge exam board. Then 12th I'll discuss some harder or challenging electric field questions from IB, International Baccalaureate, high level past paper questions. Okay, we'll do like that. If possible, I'll try to discuss AQA, OCR papers also. So after the next video, the following videos will be based on past paper discussions. Okay, I hope that will be useful for everyone. Okay, we'll meet in the next video. Bye.